In this video, we are going to talk about linear independence and non-singular matrices. The important concepts is actually summarized right here, that if A is a matrix, can be represented by its column vectors, A1, A2, up to AN, then the equation AX equals B, so this is the matrix equation, matrix A times vector X is equal to vector B, can be written in terms of columns of A. In other words, if x, the vector x, is equal to the vector x1, x2, x3 up to xn, then we can multiply each of the components of x, x1, times the corresponding column of A, plus x2, a2, plus up to xn, xn equals b. This implies that the linear system represented by A is consistent if and only if B can be written as a sum of scalar multiples of the column vectors of A. Here are the scalar multiples, the scalars multiplying each column vector are the scalars in the vector x. Thus, AX equals B is consistent if and only if B is a linear combination of the columns of A, so this is key. We will do examples of this idea, and we'll go through this idea again. We will look at the definition of linearly independent versus linearly dependent. We will do examples about linearly independent and dependent vectors. We'll have some theorems, and then finally we will talk about non-singular as well as singular matrices. I'm also going to mention on my overview slide, I put linearly dependent and then parentheses non-trivial solutions. And here I put linearly independent and parentheses only trivial solutions, because if you say these words enough times, after a while it gets really confusing. So I feel like it's helpful to have these words close together. In our introduction, I had read this extremely long paragraph here, and what I'm going to do is do an example and kind of look at where we are in the paragraph. So hopefully a paragraph will help us get our footing on everything. So here we have a matrix which we can break down into columns A1, A2 up to AN. So here I have the columns A1, A2, and A3, and you can see this is the matrix A. In other words, here's column 1, here's column 2, and here's column 3. Then we can look at the matrix equation AX equals B. So this is A, this is our vector X equals B, and here I'm going to use B equals 3, 8, 1 for our first example. So I moved these lines here down so I can insert this blue line, and what this is I just multiplied this matrix times this vector. So I multiply first this row times this column, and I get x1 plus x2 plus x3 equals 3. Then I multiply the second row times the column, and I get 2x1, 3x2 plus 4x3 equals 8. And then this last row times the column, I get minus x1 plus x2 plus 3x3 equals 1. So remember, this is the system of linear equations represented by this matrix here. And if you recall how we solve that system of linear equations is we use Gaussian elimination. So here I have the augmented matrix, which is the matrix A with my vector B, and I do my Gaussian elimination till finally I get this row equivalent matrix. So to save myself time, I didn't do all the, it's actually pretty easy, it's only 2 steps of elementary row operations to get to this matrix here. But it's row equivalent to 1, 1, 1, 3, 0, 1, 2, 2, 0, 0, 0, 0. And so what this last row tells me is that x3 is free, so it's arbitrary. You can set it to whatever you want. Then this is x1, this is x2, plus 2x3 is equal to 2. So in other words, x2 is equal to 2 minus 2x3. And then last I have x1 plus x2 plus x3 equals 3, or x1 is equal to 1 plus x3. So I have these solutions. At this point, again, there are infinite solutions since x3 is equal to free. So you can plug in x equals 0, and then you would get, that's a very easy way of getting a quick solution because x1 would equal 1 and x2 is equal to 2. But I got it in my head because I wanted to illustrate something else. I wanted a solution where x2, x1, and x3 are not equal to 0. So I plugged in x equals 3, but then x equals 1, but when I plug that in, I see x2 is equal to 0. So I tried x3 equals 2, and then I got x2 equals negative 2 from this equation. and x1 will equal to 3. So what I can do then is I can rewrite my b vector 3, 8, 1 as equal to x1 is equal to 3 times my first column vector, which is 1, 2, negative 1. My minus 2, that's my x2 times my second column vector, and my x3 times my third column vector. And now I can verify my solution of 3, negative 2, 2 by multiplying 3 times a1, and I would get 3, 6, and minus 3. Multiplying my negative 2 times a2, I'll get negative 2, negative 6, negative 2, and 2 times my last column vector, and I'll get 2, 8, and 6. And when I sum these up, so 3 minus 2 plus 2 will give me 3, my 6 minus 6 plus 8 will give me 8, and my minus 3 plus minus 2 plus 6 will give me 1. So I have verified this linear combination of the column vectors is equal to my b. And that's exactly this part, what this is saying. My ax equals b can be written in terms of the columns, a1, a2, a3, with the vectors x1, the components, the scalar multiples x1, x2, up to, in this case, x3. And just reading the rest of this, so this means the linear system represented by A, and this is the linear system here in blue, is consistent. In other words, it has solution if and only if B can be written as a sum of scalar multiples of the column vectors of A, as we did here. Here are the column vectors of A, and we have these scalar multiples, and these scalar multiples are from the vector x. We call this sum here, where we have scalar multiples of the vectors, a linear combination of the vectors. So when you have vectors and you multiply them by scalars and then add them together, that's a linear combination of the vectors. Thus, ax equals b is consistent if and only if b is a linear combination of the columns of A. So this example is a really important example to be comfortable with. So if you need to, I would go over it again or take notes and just slowly look over it and see how it fits in with this description up here. X2. And also over here, I put in the x1, x2, x3. I use this x vector when x equals 0. Right? When x is equal to 0, x1 is equal to 1, x2 is equal to 2. And you can see this linear combination also equals b. Again, because x3 is free, there's an infinite number of solutions. Just every time you choose a new x, you'll get a new solution. And remember, the possibilities for solutions of a system of equations is no solution, a unique solution, or in the case when you have free variables, infinitely many solutions. I have one more example, and that is to now use b2 as our b vector. So again, I have my column vectors of A. I wrote that down as a matrix, my 1, 1, 1, 2, 3, 4, and negative 1, 1, 3, times x1, x2, x3, my x vector, is equal to, and now I use b as equal to 2, 5, negative 1. Again, I'm going to use Gaussian elimination on the augmented matrix, which is row equivalent to 1, 1, 1, 2, 0, 1, 2, 1, and 0, 0, 0, negative 1. But now what you can see, this last row, this is times x1, x2, x3. So 0x1 plus 0x2 plus 0x3 is equal to negative 1. And there's no possible way that we can have this, that any x1, x2, and x3 can solve this equation. So this is an example of where the system is inconsistent. There's no solution. So two things that means. The two things that means is, one, the system of linear equations represented by this augmented matrix, or this matrix equation, x1 plus x2 plus x3 equals 2, 2x1 plus 3x3 plus 4x3 equals 5, and negative x plus x2 plus 3x3 equals negative 1, has no solution, right? The matrix is inconsistent. And furthermore, the second thing about this in terms of linear combinations, b, the 2, 5, negative 1, cannot be written as a linear combination of the column vectors a1, a2, and a3. In other words, 2, 5, 1 equals, this should be an equals, x1 times a1 plus x2 times a2 plus x3 times a3 has no solution, which looking back over here at our review, we said the linear system represented by A is consistent if and only if B can be written as a as a linear combination of the vectors. So again, since it has no solution, it's not consistent. That means we cannot write B as a linear, B cannot be written as a linear combination of the vectors. I cannot emphasize enough how important it is, how important this example is for you to understand these ideas. It'll take you a long way in this class. So here it is a little bit in my more abbreviated form. And here's that example crammed into my overview slide. And I'm sorry it's kind of small, but I have this obsession with getting all of my main points on one slide. So here it is, crammed in there. So now we can talk about linear dependence and independence. I moved our discussion of linear independence and dependence up here so I have a little more room. So we talk about a set of vectors, and they're m-dimensional, so they have m rows. And then we have p of these vectors. They are said to be linearly dependent if there are scalars a1 up to ap, so you can multiply each of these vectors by a scalar, and not all of which are 0, such that a1 v1 plus a2 v2 up to ap vp equals 0. So they're linearly dependent if you can find scalars a1 up to ap, not all equal to 0, but when you take the linear combination, it equals 0. And on the other hand, they are linearly independent if this linear combination a1 v1 plus a2 v2 up to ap vp equals 0 has only the trivial solution. We will look at these two other notes once we do an example. So our first example, determine if these vectors v1, v2, v3 are linearly independent or dependent. And looking at the definition, determine if this is dependent or independent, we want to know if the equation ax equals 0 have non-trivial solution. If it has a non-trivial solution, then they are considered dependent, right? Dependent means there's a non-trivial solution. If there's only the trivial solution, it's independent. And the matrix ax equals 0 looks like this. Here I've put together the vectors v, x equals 0. And now I know to solve this equation, I'll look at the augmented matrix, which is equivalent, row equivalent to 1, minus 2, 1, 0, 0, 5, negative 3, 0, 0, 0, negative 2, 0. So my first equation, my top row, is x1 minus 2x2 plus x3 equals 0. My second equation is 5x2 minus 3x3 equals 0. And my last equation is minus 2x3 equals 0. So I get x3 is equal to 0. Plugging in here, I get x2 is equal to 0. And then plugging x2 and x3 equals to 0 here, I have x1 is equal to 0. So that means there is only the trivial solution, which by my definition means these vectors, v1, v2, and v3, has only the trivial solutions. They are independent. I'm going to do one more problem to show you what it looks like when the vectors are dependent. So I've kind of given you the answer here, but let's go through it. So let's say v1 is equal to 1, 2, and v2 is equal to 3, 6. So are they linearly independent or dependent? We have to ask the question, does ax equal 0 have non-trivial solution? Matrix ax equals 0 we can solve by looking at our augmented matrix plus our b, which in this case is 0. And then we do the row reduction, and what we get is that x1 plus 3x2 is equal to 0. So x1 is equal to negative 3x2. So one possible solution is let x2 equals 1 and x1 is equal to negative 3. And you can see that negative 3 times our first column, v1, plus 1, that's x2, plus v2, our second column vector, 3, 6, will be equal to 0. And I really wanted to do this example because I wanted to say that when vectors are dependent, one vector can be rewritten in terms of the others. So in terms of this example, we can see that that v2 can be rewritten as negative 3v1. And in general, when we have this equation, because if they are dependent, so that is if they are dependent, here we are. If they're dependent, we can look at this equation, a1v1 plus a2v2 plus apvp, right? And not all of these a's are 0. So whichever ones are not 0, if they're 0, we're going to throw those terms out. But the ones that aren't 0, the ones that are left, we can then solve for any of the ones that are left without the zeros in terms of the other vectors. So for example, if we wanted to solve for v1, we can subtract minus a1 v1 from both sides of this equation, so we get negative a1 v1 on this side of the equation, and on the other side of the equation we have a2 v2 plus ap vp over here. And then because we know a1 is not equal to 0, we can divide both sides of the equation by a1, and then we have solved for v1 in terms of the other vectors. Again, we have to throw out the ones that the coefficients aren't equal to 0, so we can do this division. So coming back to this note, to determine if a set of vectors is independent or dependent, we solve the homogeneous system of equations ax equals 0. If the trivial solution is the only solution, then it is dependent. Trivial solution, then it is independent. Otherwise, it is dependent. And the analogy I like to use are colors, and actually it's actually stronger than an analogy, and I'm going to use this analogy throughout many of my slides, or videos, so you might as well kind of get used to it. So let's say we have three vectors, v1, v2, v3, and let's say v1 represents the color red, v2 represents the color yellow, and v3 represents the color orange. Then I would say v1 and v2 are independent because you can't make red from yellow or vice versa. But you can make orange from yellow and red, so I would say orange is dependent on red and yellow. And in fact, I would say that V3 is a linear combination of red and yellow. And you can mix different amounts of red and yellow, and that's the different amounts is represented by these scalar quantities x1 and x2. So if there's a lot of x1, if x1 is high and x2 is low, that means it's a very reddish orange. But if x1 is low relative to x2, then it's more of a yellow orange. So dependence, though, in this case, we are going to talk about this more, but in this case, to be dependent means you can make one of these objects from the other two. And technically, if we can subtract things out, and for our study of linear algebra, we want to say technically we could make red, or V1, by subtracting out our yellow, V2, from our orange. So red equals orange minus yellow, right? If we could take the yellow out of the orange, we would be left with red. And then vice versa. You can make yellow out of orange by subtracting the red. So these three are dependent. They have some sort of dependencies on each other. These two by themselves, V1 and V2, they aren't dependent. They're independent. But as a set of three, they are dependent. And now returning back to this note, hopefully this will make it more clear that dependent means one of the vectors can be constructed from the other vectors. And just a quick note, red, yellow, and blue are all independent because you can't make one from the other, and you cannot make one from the other two. So no matter how much you combine red and yellow, you'll never get blue. No matter how much you combine red and blue, you'll never get yellow. And no matter how much you combine yellow and blue, you'll never get red. And also just a quick note, they are also a basis for the other colors. In other words, if you name any other color, you theoretically, if you're good at mixing colors, can make any other colors from these three colors. That's why they're considered a basis. But we'll talk about bases like in another chapter. Our next example is to, without solving the corresponding homogeneous system of equations, show the set is linearly dependent. V1 is equal to 1, 2, V2 is equal to 3, 1, and V3 is equal to 2, 3. And I am going to give you a hint, since this is going to be like a proof, or sort of like a proof. You are going to be using theorems, including one from our previous video when we talked about consistent systems. And just a quick note, so I'm not going to solve the corresponding system, but I am just going to write it down, or write it out. So I have my x1, 3x2, 2x2 equals 0, my 2x1, my x2, and my 3x3 equals 0. And I'm going to note that there are two equations, so m is equal to 2, and there are 3 unknowns. N is equal to 3. And from our last video about consistent systems, that was chapter 1.4, we had this theorem. So for homogeneous systems of equations, in this case it's homogeneous because it's equal to 0, when m is less than n, then a homogeneous m by n system of linear equations always has infinitely many non-trivial solutions when m is less than n. So since m is less than n, this system has infinitely many non-trivial solutions. Therefore, it is linearly dependent. Which leads us directly into our next theorem over here, which I just immediately moved up here so there'd be room for a proof, which says if the number of vectors is greater than the number of rows, then it is dependent. So the theorem says let v1, v2 up to vp, so they're p vectors, be a set of vectors in Rm. So there are m equations. So each of these vectors go down, they have m components. Then if p, the number of vectors, is greater than m, the number of rows, then the set is linearly dependent. These vectors are linearly dependent. And our proof is going to follow almost exactly what we did in our previous example. We're going to say the set v1 through vp is linearly dependent if vx, the v being the matrix of these vectors, equals 0, has non-trivial solution. We note that V is an M by P matrix, where P is greater than M, and then using the same theorem we did for our last problem, we say that since M is less than N, in other words, the number of rows is less than the number of columns, and that's exactly here, the number of columns is greater than the number of rows, then Vx equals 0 has infinitely many non-trivial solutions, and therefore V1 through Vp is linearly dependent. So this is a proof you should be very comfortable doing. And of course, it depends on you knowing this theorem here. So you should know this theorem, and you should know our new theorem, and also be comfortable proving our new theorem. And now we are ready to talk about singular and non-singular matrices, as well as this theorem here. The definition of a non-singular matrix means it has only the trivial solution. And the definition formally is an n by n matrix A is non-singular if the only solution to Ax equals 0 is x equals 0. And A is singular if it is not non-singular. In other words, it has non-trivial solution. And something important to note, at this point we are talking about square matrices. In other words, n by n, where the number of rows equals the number of columns. Our first example is to determine if these two matrices are singular or non-singular. So our first matrix is 1, 3, 2, 2, and our second matrix B is 1, 2, 2, 4. So for matrix A, I put together the augmented matrix, with the 0, 0 vector here, the solution vector. So I have, to row reduce it, I have E2 minus 2E1, and I get 1, 3, 0, 0, negative 4 is 0, and this gives me 0 times x1 plus minus 4x2 equals 0. So that means x2 is equal to 0, and then my top equation means x1 is equal to 0. So there's only the trivial solution, which means A is non-singular. For matrix B, I have the augmented matrix here, and it row reduces to 1, 2, 0, 0, 0, 0, which means x2 is free, and x1 is equal to minus x2, which means there are non-trivial solutions, in fact infinitely many, but non-trivial solutions, which makes matrix B singular. Next we have the theorem that says an n by n matrix A, which is equal to the column vectors A1, A2 up to AN, is non-singular, in other words, has only the trivial solution if and only if A1, A2 up to AN is linearly independent. And remember, linearly independent means it has only the trivial solution. So this proof should be fairly straightforward to do and really depends on your understanding of linearly independent. And so give it a try, but I do have a proof for you on the next slide. Here is our proof. So we'll start with the forward direction. That is to prove that this matrix, if it's non-singular, that implies the column vectors are linearly independent. So we'll start with A is non-singular, again, proving the column vectors are linear independent. So A is non-singular means that AX equals 0 has only the trivial solution, and I'm using the definition of non-singular here, x equals 0. So I'm rewriting AX equals 0 in this kind of matrix form. I've expanded the matrix, so I have the matrix A times x equals 0, 0. And then I also note these are column vectors, so this first column is A1, the second column is A2, etc. Next, what I'm going to use this theorem from a previous video, the 1.5 on matrix operations, that told us if we have a matrix made up of column vectors, and all matrices are made up of column vectors, it's an n by n matrix whose jth column is aj, and let x be the nth column vector, the n by 1 column vector, x1 up to xn. Then the product a times x, which is what we have here, can be expressed as x1 times the first column plus x2 times the second column plus xn up to xn times the nth column. So I've re-expressed this using this theorem here. So this theorem is very straightforward, but you do have to know this theorem, which is a good one to know. So here I have this expressed, and again, it's just a re-expression of this equation here, which has only the trivial solution. So this expression has only the trivial solution, and by the definition of linearly independent, that means the vector a1, a2 up to an are also linearly independent. The proof in the other direction just is sort of like backwards here, right? You start off with these vectors being linearly independent, which this is the definition of a1, a2 up to an being linearly independent, but this is just a re-expression of this matrix equation, and this matrix equation having only the trivial solution is the definition of non-singular. And here is an important theorem for n by n matrices. An equation ax equals b has a unique solution for every n by 1 column vector b if and only if a is non-singular. So if a is non-singular, then this equation, no matter what b is, always has solution. The proof in the forward direction is very straightforward. So we're going to start with the equation ax equals b has unique solution, and we want to show that a is non-singular. Well, axb has unique solution for every b. If we let b equal 0, then ax equals 0 has a unique solution. And it has to be the trivial solution because the trivial solution is always a solution, which means it has only, if it's a unique solution, it has only the trivial solution, which means it is non-singular. For the other direction, we are going to be proving that if A is non-singular, then AX equals B has unique solution for every vector B. So we're going to consider the column vectors of A, and again, that's non-singular. So we're going to consider now the column vectors of A along with the vector B. So the number of vectors here is n plus 1, right? Because we have n column vectors of A plus 1 vector B. And that's going to be greater than the number of rows because remember, this is an n by n matrix. So if we have the number of vectors is greater than the number of rows, then we know the set is dependent. So that means this set of vectors, the column vectors of A along with B, is linearly dependent. And to be dependent means that if we multiply each one by a scalar, a little a1 times column a1 plus little a2 times column a2 up to the scalar an times the column an plus the scalar an plus 1 plus the column vector b is equal to 0, we have a solution where not all the a sub i's are equal to 0. And since a is non-singular, that means without the b, then everything would be 0. That must mean that an plus 1 is not equal to 0. So we can solve for b in terms of our column vectors a1 through an, and here's our formula, which means that ax equals b is consistent and has a solution. To show the solution is unique, we're going to do a proof by contradiction and assume we have two solutions, x1 and x2. That means ax1 is equal to b and also ax2 is equal to b. So ax1 minus ax2 is equal to b minus b is equal to 0. We can also then factor out by our matrix properties. We can factor this so that it's x1 minus x2 equals 0. Since a is not equal to 0, that means x1 minus x2 is equal to 0, which means x1 is equal to x2, meaning that there really is only one unique solution. Now we have covered the main material of our video, which was about linear independence and non-singular matrices. So this was a really good summary of our video. So if we have a matrix A, which can be written as column vectors A1, A2 up to AN, the equation AX equals B can be written in terms of the columns of A. That is, B can be written as x1 a1 plus x2 a2 plus xn an. And actually this we got from a previous video when we talked about matrices and this matrix equation. But this implies that the linear system represented by A, here, that ax equals b, is consistent if and only if b can be written as a sum of scalar multiples of the column vectors of A, as we have here. B is written as a sum of scalars times the scalars x1, x2, and xn times the column vectors a1, a2 up to an. Thus, ax equals b is consistent if and only if b is a linear combination of the columns of A. We had two examples here, one where we could write the linear combination and one where we could not. So one where we have a consistent system and one where we have an inconsistent system. Then we talked about linear dependence and independence. So a set of vectors, v1 to vp, is said to be linearly dependent, in other words, has non-trivial solutions to this linear equation here. When you multiply each of the vectors by a scalar and then set it equal to 0, it's linearly dependent if they're non-trivial solutions. And it's linearly independent if it has only the trivial solutions. In other words, all these scalars have to be equal to 0. And then thus, to determine if a set of vectors is independent versus dependent, we saw the homogeneous system of equations, which is represented by ax equals 0. And if the trivial solution is the only solution, then it is independent. Otherwise, it is dependent. And we have an example here. And we also want to note that dependent means one of the vectors can be constructed from the other vectors. So here we have this vector. This is from this previous example. This vector is a linear combination of the other two vectors. Because they are dependent, we can do that. We have this theorem where the number of vectors is greater than the number of rows will imply a dependent system. We talked about non-singular matrices, which have only the trivial solution for the ax equals 0. And it is singular if it has a non-trivial solution. And again, for singular, non-singular matrices, we're depending with n by n matrices. We have this theorem for n by n matrices. It's non-singular if and only if the column vectors are linearly independent. And second, if A is an n by n matrix, the equation ax equals b has a unique solution for every column vector b if and only if A is non-singular. For review, I have 4 problems for you to try. Pause the video, give them a try, and on the next slide, I will have solutions. This is the solution for the first problem, the solution for the second problem, the solution for the third problem is here. This is the solution to the last problem. And that's it for this video. Thank you for watching.